All right. Now we're going to consider, in many ways, the other half of the topic of electromagnetism, magnetism. But we're only going to spend a couple weeks on this, though that nonetheless should not detract from the fact that this is kind of the flip side of a coin. Right? You have electricity and you have magnetism that combine to form electromagnetism. And so, in considering magnetism, we can start by kind of grounding our intuition with our understanding of permanent magnets. Magnet kind of like this. I have kind of this simple toy magnet here, where you can have things that through some sort of long-range force, like we were talking about with the electric field and the electrostatic force, but in this case because of magnetism, these magnets can interact with one another in a way where they don't have to be touching one another and can still nonetheless interact. And so the idea of the magnetic field, and again, this has been known for centuries, that there were these lodestones that people would have that realized that there was some permanent magnet attached to it. I don't think they called it a magnet, but they knew that there was some interaction with these particular metals that would occur with lodestones and things that have permanent magnets attached to it. And then bar magnets, of course, are kind of the example of that we know about today. The reason for how bar magnets work, actually, it takes a little quantum mechanics, actually, in order to fully understand kind of how a bar magnet works. It has to deal with the quantum mechanical nature of the electrons and the fact that they have spin. So we won't really delve into that too carefully. We'll save that for modern physics. But we will step back a little bit and think of another kind of description of magnetism, and that magnetism requires the motion of moving charges in order to interact, which might not seem very intuitive, because you think I can have two bar magnets, and I can put them close to one another. When I drop it, I have two bar magnets and I put them close to one another. They can interact. It doesn't seem like I ever need anything to be moving in order for these two things to interact with one another. But deep within, right, there is some motions going on with the electrons spinning around as they try, within the nuclei of the molecules and atoms. Now, what we'll be talking about, in this part of the course, actually was discovered somewhat accidentally. Kind of in the 19th century, Oersted, was studying, circuits and an electric current, and he noticed that his magnetic compass that he had would always fluctuate whenever he had wires with current flowing through them nearby. Conversely, he then realized that magnets seem to affect the currents that were flowing through these particular wires. So it seems like there was some connection between moving charges and magnetism. But before we get to that, let's see if we can try to come up with a reasoning of how we might define the magnetic field. And we can start again with a bar magnet. So you have a bar magnet that has two ends. And you have another tiny little magnet. So I have this little magnet here that has a blue end and a red end. And if I take some magnet, I can realize that if I put the other magnet nearby, the magnet orients itself such that it can, let's see if I can do this aligned. It can orient itself such that as I move the magnet around, it seems to trace out a particular path that kind of loops around, comes out of the top and loops around to the bottom. And then if I do it on the other side, it does the same sort of thing, kind of on the other side of the magnet. And you can imagine taking like a tiny little compass and putting the compass here, and notice that the arrow kind of points this way, and the arrow here might point that way, arrow here, and you start to get a sense of that there is some directionality going on here. That the two magnets do seem to interact with one another, and the tiny magnet rotates itself in a particular direction. So the tiny magnet The tiny magnet here is playing kind of the role of the test particle. Think back to when we did electric fields. We had some electric field that we were trying to discover from some distribution of charges, and then we would put a tiny test particle, meaning that it wouldn't disrupt and make the other charges move around, but we would just then measure the force that that particular test particle felt, and that would then define the direction of the electric field. We're essentially doing the same thing, but using a tiny little test magnet. So these tiny magnets orient themselves in some external magnetic field. And the symbol we use for the magnetic field is B. Why not M? Well, you can thank Maxwell for that. M was already being used for other things, and so he kind of opted to use B when describing magnets. And given he is kind of the king of electromagnetism, because this culminates in Maxwell's equations, B has stuck. So by doing this, we can, from a test magnet, get a sense of the direction of the magnetic field. For a bar magnet, it looks something like this. Where it seems like the magnetic field comes out of one end and then goes towards the other end. And we can then make conventions. We can call one end the north end and one end the south end, and have that define a direction. Make a convention that the magnetic field points from north to south. Just like how we made a convention that electric fields come out of positive charges and go towards negative charges. So, convention B points north to south. So that helps us get a sense of the direction of the magnetic field, that we can assume, that we can again posit that, like the electric field, there is this invisible field, which is a way for the magnets to convey their presence to the rest of the cosmos. That they don't have to, they can interact with things that they aren't touching using the same concept as a field, but in this case, the magnetic field. Now, if you want to try to get a sense of the magnitude, there it gets a little bit more challenging. For a bar magnet, you might think of, you probably did this in high school, where you can take a magnet and you can sprinkle iron filings all around it, and you would see that they kind of clump together near the poles and kind of get more spread out away from the poles. Maybe I can quickly pull up a picture of this. Let's see, iron filings magnet. No, I do not want to buy one. Let's see. Come on. So here's the idea. Right, we can kind of move this here. Right, the idea is that you sprinkled some iron filings around a magnetic bar magnet. Notice that they tend to cluster near the poles, so you might take, you can take that to mean that the magnitude of the magnetic field is likely stronger there. And then, as you were to go farther and farther out, if you were to go farther out, you would be able to tell that the magnetic field does seem to get weaker as you get away from the magnet, and the iron filings do tend to align with the lines of magnetic field that we drew in the previous picture, the one kind of right there on the left. So that suggests we're on the right track in terms of being able to describe the magnetic field. And then if you do this more carefully, you can then start to draw the magnetic field for more complex magnetic arrangements. So I have, for example, the idea of two bar magnets. If I put that there, you can then start to draw what the magnetic field might look like for two different bar magnets. And there, you notice that the magnetic field lines do kind of give a sense of the things that we kind of have some intuition for. If we look at the alignment right here, it almost as if, I can kind of see that there is an attraction between the two magnets, and that these two ends are going to try to snap together, because the magnetic field lines kind of connect them through space, versus the magnetic field lines here, it almost feels like they're trying to push away from one another, and and there's going to be a repulsion here. So then that brings up the results that we're familiar with, where like poles repel and opposite poles attract. Again, still very analogous to what we experience with electric fields and positive and negative charges. So, all of this is well and good, right, and kind of matches what you're familiar with already. So, excuse me. But now let's see how we can quantify, a more fundamental definition of magnetic fields. So magnetic fields require moving charges. To exert forces. Or rather, the magnetic field acts on, a moving charge can feel the force from the magnetic field. And again, once you get into the quantum mechanic realm, this idea becomes a little bit more subtle when you think about things spinning and whatnot. But again, we're going to stick kind of macroscopic, and we're going to just think of moving charges, electrons, protons, what have you, and how they experience a magnetic force. And you can test this, of course. You could have a magnetic field, or something has a magnetic field around it, even though you might not know fully how to define it yet. And you can put a single charge that's not moving, somewhere in the vicinity, and you would see that it would just sit there. It would not experience a force. But then when you try to shoot a charge nearby or through the magnetic field, you would notice that it would respond to the magnetic field. And we can actually use this to have a more kind of clearer fundamental way of defining the direction and magnitude of the magnetic field. And again, this is very similar to what we did for the E fields. So just as a quick aside, remember for E, we defined E. What did we do? Right, E, which is we define as F divided by Q. For some sort of test charge Q, where we would have some external magnet or some external electric field, that we didn't quite know, and we would be able to draw these lines because we would place a test particle kind of in its vicinity and measure the direction of the force on that test particle. And then we can use this to define a direction and magnitude of the electric field, for example. That's, again, quick aside. You can go back to whatever lecture we did to define that if you need to review. So, what we're going to do here is to define B. We're going to do the following. We're going to shoot charges. We have some region. So we define B in a region by shooting charges through that magnetic field in different directions. And the idea is that we have this quantity Q, which is the charge, and then there's also associated with it a velocity V, which then corresponds to how fast it's moving and what direction it's moving in. And so suppose you did something like the following. So we have some region here. Where there is a magnetic field in between these two plates, or in this kind of volume, say. And we're going to just shoot charges through this region and monitor the direction and magnitude of the force that charge then feels. Again, we could place it stationary and notice that there is no force that it feels. So it does have to be moving. When V is 0, we might even write it down as one of our experiments. when v is 0, seems like f equals 0. That's kind of maybe experiment 0. Experiment 1 might be we take QV and shoot it in this direction. And suppose when we do that, we notice that as soon as it enters the region where there's this magnetic field, the force, or sorry, the particle starts to accelerate into the page. So maybe that's our observation that we observe. And we're going to take Q to be positive in all of these cases. Observe that F points into the page. Okay, that's an observation. And if I do it with different magnitudes of the velocity, I notice, that changes the magnitude of the force. If I double V, it seems like I double F. If I double Q, it seems like I double F. All right, that suggests that this QV probably isn't going to be in the numerator, for our ultimate expression. Experiment 2, maybe I do it the opposite direction. In experiment 2, I notice the same thing, but F points out of the page. When I do that experiment. Then suppose for experiment 3, move this over. Experiment 3, perhaps I do it at an angle. And do it at some angle relative to the to the vertical. And when I do that, I notice that F still points into the page. And the magnitude of F seems to depend on the sine of that angle. Now sine, review of sine. Sine of 0 is 0, and then sine of 90 degrees is 1. So then that's saying that the magnitude of the force is greatest when the charge was moving horizontally. Then as it becomes more and more vertical, it gets smaller and smaller and smaller as that angle gets smaller. Such that experiment 4, when I just shoot it straight down, I notice that the charge does move, but it doesn't seem to accelerate. So I notice that F seems to be 0 in that case. There's no change. Now all these experiments are showing something interesting. It seems that the force that the thing feels, if there's a force at all, is perpendicular to the velocity. And when it was moving horizontally, the force pointed either in or out of the page, at a 90-degree angle. When it was going at an angle, like experiment 3, the force still was perpendicular in and out of the page. I could also have done a different angle, veered upwards. I would have gotten very similar results. And the force would have pointed out of the page in that case. Well, I guess, for experiment 3, it would have always pointed into the page. Experiment 2, if I did it at an angle, it would have pointed out of the page. And experiment 4 seems like there's no force at all. So this is already different than the electric field, in that the force in the electric field were always kind of parallel or anti-parallel in that case. Now it seems like the force is perpendicular to the motion of the particle. But we still haven't quite defined, how does this define a magnetic field? Well, we can use this as a way to define the direction of the magnetic field. So from these observations, we can make the following convention conclusions. From these, we can conclude that the force seems to be perpendicular to V. If it experiences a force from a magnetic field, it seems to be perpendicular to V. And the magnitude seems to depend on Q and V as well. right, magnitude of Q, and then the magnitude of V. But there was a particular direction, and that the force did have the sign dependence, and that the force had the sign dependence on its directionality. So what we can do is define the direction of the magnetic field to be the direction where that charged particle experienced no force even when it was moving. So to be the direction it experienced no force, as it moved. So in this case, it seems like we would define the magnetic field as pointing downward. And then we can define the magnitude to be, in all of these cases, where we can define the magnitude B to be the value of the force divided by the magnitude of Q times the magnitude of V when the particle moves perpendicular to the direction you define by the magnetic field. So again, because there's that sign dependence, means I can shoot the particle in different directions. I'm going to get different magnitudes of the force, but we can identify through these experiments that if I define the magnetic field as downward, that it seems like the force is maximized when the velocity is perpendicular to the magnetic field. We can take that, right, that's when sine equals unity, when theta equals 90 degrees. We can take that as the definition of the magnitude of the magnetic field once I divide out the charge and the velocity as well. So this all seems way more complicated than what we did for the electric field. And admittedly, this is not perhaps the most fundamental way of defining the magnetic field, but this is how we can do it kind of based on experimentation. We need relativity and stuff like that if we really wanted to do a more fundamental definition of the magnetic field. But through experimentation, which science is all about, physics is all about, this is a way that we might come to be able to define the magnetic field. Mathematically, this can all be encapsulated in a more simple expression. So this all is satisfied if we define the magnetic force as the following. That the magnetic force from the magnetic field, F sub B, is equal to Q, velocity vector V, and then we're going to do the cross product of V with the magnetic field direction B. And so this time symbol is the vector, or sometimes called the cross product. It is not the dot product, but it is again a way of multiplying two vectors together. And I'll point out, just in case I slip up, I kind of like the European convention for the cross product, because again, this cross symbol or the time symbol, right? Sometimes you do have the variable x flying around as well. And so sometimes, like, is that an x or is that a cross product? So if you ever see me write it with a chevron instead, that again is also saying the cross product, which I kind of like better, admittedly. But I'll stick with the American convention. So we can define the magnetic field, I'll copy it here, as Q, V, cross B, such that the magnitude of this cross product ends up being Q, V, magnitude of B, multiplied by the sine of the angle between V and B. So again, this is V, and this is B, then this angle here is what gets plugged in there for the sine. Now this looks kind of similar to a dot product, where it was the magnitude of the two vectors multiplied by the cosine of the angle between them. For here we have the magnitude of the two vectors multiplied by the sine. Indeed, the vector product and the dot product are kind of two tools that have kind of similar but nonetheless different goals, and it relates to kind of plucking out parallel components and plucking out perpendicular components, which will be the rest of this lecture, kind of just exploring this cross product. Before we get on to do that, though, physics-wise, this also defines the unit of the magnetic field. So the unit of B we can define by this definition, where it looks like it's going to be the unit of force divided by the unit of charge divided by the unit of velocity. So it looks like it's a Newton, Coulomb, meter per second. And we define that to be the Tesla. After the person, not the car. So that is the unit of the magnetic field is given usually in terms of Teslas. And just give you a feel for some of the numbers. So in outer space, kind of far from any object, the magnetic field is kind of on order of 10 to the negative 10 Teslas. On the surface of the Earth, it's about 10 to the minus 4 Teslas. Just from the Earth. The Earth has a magnetic field, which kind of looks like a bar magnet in the middle of the Earth. It kind of comes out from the North Pole and goes into the South Pole. Roughly, rather. Kind of a toy, a bar magnet. Kind of is 2 orders of magnitude up, kind of 10 to the negative 2 Teslas. And then a big electromagnet is kind of on order 1 Tesla. So 10 to the 0. Just give you a sense of a feel for some of the numbers here. So that's the idea. Now, in order to evaluate this force, it seems like we need to get more acquainted with how we evaluate this cross product or vector product and some of the properties that are associated with it. So, the vector product. So again, we've already seen the example of a product that involves 2 vectors, which was the dot product, where 2 vectors went in and it popped out, in that case, a scalar. Right, the motivations of the dot product. Let's use a physics example of work. You're some person, they're trying to pull a box across the floor. You're exerting some force along the rope that's attached to the box, and you ideally want the box to move to the right in some way as you pull. Now, your force, not every part of that force vector contributes to moving the box to the right. In that case, you have a force vector that is kind of at an angle, and then your motion is horizontally to the right. There's some angle between them. And the component of F that actually contributes to the motion to the left and to the right is the part of F that is parallel to the motion. This part here, this component of F that is parallel to dr vector motion is actually what contributes to your horizontal motion. And so we defined the dot product in a way that essentially the geometric definition of the dot product is that it can pluck out the part that is parallel to another vector. So that's when I do f dot, say, r hat. The way I define this in upper level mechanics is that I define the dot product as what this does is this gives me back the part of f that is parallel to the unit vector r hat, which, if you look at the drawing up above, right, would be something like f cosine of theta. And then you can generalize the dot product so that when you take kind of a dot b, the general definition then is magnitude of a, magnitude of b, times cosine of the angle between them. Or if you want to think of it, if I rearrange it a little bit, right, you can see that it seems like it's the magnitude of b times the component of a that is parallel to b. So the dot product has a way of extracting parallel components relative to another vector, right? It doesn't have to necessarily be a horizontal or vertical axis, right? You give me any two vectors, I can tell you the part of one vector that is parallel to the other. And of course, then we saw that manifest itself in the work energy theorem, for example. The change in kinetic energy was equal to the integral of force dot dr, which again, what is this integral saying? It's you're adding up the components of f that are parallel to the direction of your motion. So you're adding up all these f parallels to your motion. And you can go back to one of the potential lectures where I went into all that in detail. Right, and then the point being that when you had things like when the dot product was 0, that meant there was no parallel component, which then was a way for you to tell whether or not two vectors are perpendicular to one another. Right, if a dot b equals 0, then that means that A is perpendicular to B. Because in that case, there is no parallel component to extract. And then you get all the nice definite, all the stuff related to energy and work. So again, that you can think of that as kind of like a physical motivation of why we should need something called the dot product. Why would we need something called the cross product or the vector product? Well, let's do a motivation with that. Let's see. So what's a motivation here? Well, let's use a classical example, or rather a mechanical example. Suppose you have a wrench that is wrapped around a screw. You have some screw here. Now, if you want to screw in the screw, that's done by rotating the wrench around and twisting it in. So, for example, if you exerted a force on the screw in this direction, I just had the wrench and I just kind of pulled and tugged on the wrench, obviously that does nothing. That's not going to get the screw to screw in or out at all. Instead, if you exert a force that, say, is something like this, at some sort of angle, then that might not be the most efficient way to make the screw in, but you can convince yourself that if you exerted a force like that, in that case, then the thing would start to rotate around. There would be motion that would occur as a result. It would not be speeding up, slowing down, in the kind of tangential way like we were thinking about with the dot product. But there would be some motion that would start to occur in some sort of rotating way. And if we define this vector here, r, as the moment arm, then what results is motion perpendicular to r. If we define that r vector as the vector that kind of always points from the screw out to the edge of the wrench, then as the thing rotates around, the motion of the wrench is always moving perpendicular to that moment arm. And you could test this out more thoroughly and identify that if you have some moment arm here, and you have some force here, some angle, that what actually causes this rotation is not the component of F that is parallel to R, but the component of F that is perpendicular to R, or, unsurprisingly, F times sine of the angle between them. That component results in rotating motion. So rotation, right, results from components that are perpendicular, in this case to the moment arm, for example. Whereas speeding up and slowing down, that involved components that were parallel to your motion. And this, again, you can go back to the potential lecture and think about this, right? Because we argued through simply kinematics that for something to speed up or slow down, the acceleration has to be parallel to the velocity vector. For something to change direction, the acceleration has to be perpendicular to the velocity vector. So in this case, for rotation, you have accelerations that are always perpendicular to the velocity. Or I guess in this case, always perpendicular to this kind of moment arm if we're going to stick with a wrench. And the velocity, of course, but to stick with the picture. So, okay, that kind of motivates that there might be some vector product that is necessary to pull out, the component that's perpendicular compared to the dot product where it pulled out the parallel component. But there's also motivation that when we are pulling out this perpendicular component, that we should also return back a vector rather than a scalar value like the dot product does. And again, we can use rotation as a motivation. So rotation, suppose I have a spinning disk, and it's spinning kind of in this direction. Each element of that disk has its own velocity vector and its own position vector. And to describe their motion, and they're constantly changing as the thing is rotating. It would be nice if I had a single vector that could describe rotation in a way that maybe the magnitude of this vector gives me some sort of angular velocity, because the actual velocities differ. Right? Think of a CD or a DVD. If it rotates once a second, which is very slow for a DVD, but if it rotates once a second, that means each piece of the DVD has to complete 2 pi radians every second. Now, that's a quantity that's the same for everything on the DVD. But if I take, say, something near the center of the CD, it has to trace out a very small circle in 1 second, versus the edge of the CD has to trace out a much bigger circle in the same amount of time. That means the outside is moving much faster than, say, the inside. So the velocity is maybe not the right way to describe it. Position is not the right way to describe it, because they're all changing in different ways for the spinning disk. So instead, we can define this rotation vector, which is written with omega, that is perpendicular. So this omega is perpendicular to the rotating motion. So notice that omega is perpendicular to r, the position vectors of anything on that disk. And omega is perpendicular to v, all the velocities for the things on that disk, such that the magnitude might give you the angular velocity, which is the same for everything on that disk. And the direction of rotation is given by the right-hand rule. I'm assuming this is review from Physics 1, but it's always good to review this stuff. By right-hand rule. There's an H, not an A. And this thing doesn't squeaking as much anymore. That's good. So again, the idea here is that you point your thumb in your right hand thumb. So I realize that my screen is probably flipped for everyone. But this is my right hand. My right hand thumb is pointing straight up in the same direction of omega, and then I let my fingers, imagine kind of my fingers curling around my thumb. That gives me a sense of the rotation. So notice with the arrows I drew on that page, if you imagine putting your thumb kind of in the direction of omega, it does seem like as I curl my right hand fingers around, it's matching the rotation that you see in that disk. So that's kind of the one, there are two versions of the right hand rule. Here, that's one of them. That for rotation, you can kind of use, when you want to describe the rotating motion, your thumb sticks in the direction of this rotation vector, omega, and your fingers curl around. So then notice, if I were to flip my finger the other way, the rotation is in the opposite direction. So that is why. That's how that can be meaningful. But again, the takeaway here is that what's causing this rotation, if I want to think of it in terms of forces and things speeding up or slowing down, if I want to think about how omega might be changing, then it's the forces that are perpendicular to this motion that are going to matter, which means there might be a sign involved. And if I want to describe how omega is changing, then I might want the result to return back a vector that is pointing kind of parallel or anti-parallel to omega when I do these calculations. So here, these are some motivations that, when we're dealing with these kind of perpendicular motions, that we might want to also return back a vector that is perpendicular to where all this motion is occurring. For example, this kind of, the opposite direction, but you can describe the velocity in that spinning disk right there as the cross product of omega and r. So if you have a particular, well, I guess we haven't gotten to how to describe rotation yet, but if you are, you can come back to this, right? So if this is r, you can calculate that the cross product at this point here is going to point into the page, which kind of matches the direction those arrows are moving. Where then if I drew a position vector out here and calculated the velocity at that point on the left, then when you did the cross product, it would point out of the page. Okay. So how much room do I have? So now with motivations kind of hopefully created, let's actually go into the computational components of the vector product or the cross product. So the vector product, where we're going to have two vectors A and B, and we're going to want to calculate C, which is A cross B. We can define, as we did above, the magnitude of the cross product to be magnitude of A, magnitude of B, times the sine of the angle between them. So again, very similar to how we define the cross product, but with a sine instead of cosine. So again, it is plucking out the perpendicular components compared to the parallel components. Where again, this angle is something between 0 and 180 degrees for the two vectors. And so note when you do that, this magnitude is always positive, as magnitudes have to be. Okay, so that gives you the magnitude. Let's see. Yeah, maybe we can do the example first before I do the computational version. So suppose we have, so let's do an example where we have enough information to do this. Suppose I have two vectors. We have A, which is being described as that it has a length of 15, and it makes an angle of 75 degrees counterclockwise from the x-axis. Then I have another vector b, which has a length 10, and then it only makes an angle of 25 degrees from the x-axis. And then the question is, why did it zoom out? What is the magnitude of the cross product A cross B? Then we'll come back and actually try to figure out the direction once we learn a little bit more. So in this case, I would start by drawing a picture. And it looks like I could have vector A, which might look something like this. That's more than 45 degrees, so maybe that's around 75 degrees. Then we have vector B, which is not as long and only is maybe 25 degrees. So maybe something like that. And again, here is 25 degrees. So by advanced mathematics, the angle between them seems like it's only 50 degrees. So I know the magnitudes of both, and I know the angle between them, and I'm off and running. So then it looks like the magnitude of C, which is going to be then the magnitude of A, magnitude of B, hence the sine of the angle between them. If this is 15, this is 10, this is sine of 50 degrees. At the end of the day, when I plug those all in, I get 114.9. Which you can, check here for yourself. Okay, so magnitudes, step one. What about direction? And maybe I can label these 1, 2, and 3. So let's see. Let's move all of that down here. Oh dear. Pull this with it. So 1, talking about magnitude. Let's think about direction. So the direction is then given by the right-hand rule. And kind of the other version of the right-hand rule, where you're not kind of curling your fingers around your thumb, but you're using you're kind of curling your fingers and then looking at the direction of your thumb, and your thumb is the answer. So the way I like to do it, some people do it with this thing that kind of involves you kind of doing something like this, where you have 3 fingers pointing perpendicular to each other. I don't quite like that because it's not required that the vectors are always all 3 vectors are perpendicular to each other. So here, the way I do it is, to compute the direction of A cross B, take your right hand and start by pointing the fingers in the direction of A. So if A is pointing this way, I can take my right hand and start with my fingers pointing in the same direction as A. Knowing that it might, let me write the next step down. And then sweep your fingers to point in the direction of B. And then your thumb is pointing in the direction of A cross B. With the disclaimer of you should not break your knuckles in the process. What do I mean? Okay, suppose we have two vectors. I can do this so that even if it's flipped, it should look correct. So I have two vectors, A and B. So I would start by taking my right hand, my fingers, and pointing them into the direction of the first vector, A. And then sweep my fingers without moving my hand so that they're then pointing in the direction of B. So it starts with A, sweeps over to B. My thumb then points in the direction of the cross product, which would then be out of the screen. So again, starts with A, sweeps over to B. I look at where my thumb is doing. That's the answer. Notice if I had my hand, I'm going to break my wrist doing this. Notice if I had my hand like this, I couldn't really stretch my fingers back, without kind of risking breaking my knuckles in order to get, starting at A and pulling them back to B. So again, if you're in pain, it might be that you just have to flip your hand around or rotate your piece of paper. It should be the natural way for you to start with your fingers in one direction and sweep it to point in the direction of the other vector. And always use your right hand. Left-hand people like myself, rejoice. We can do this, because every time on an exam, this always happens, where people are writing it down and there's a question that needs the right-hand rule, and all the right-handed people bring up their left hand and then start doing it so they don't have to put the pen down, and then they get the wrong answer. Us left-handed people, we can keep writing while still doing the right-hand rule. We have, we're a dying breed, right? We have to savor these small victories. But again, the takeaway for that is that always make sure you're using the right hand, else you do get the wrong answer if you try to use your left hand. So, back to this example. For this example, again, I can't really do it on the screen, but could start with my fingers kind of pointing in the same direction as A, and then the natural, and I could think, which way should I orient my hand so that I could naturally curl my fingers to then sweep down to point at B. If I do that, I notice that my thumb points into the page. So here, the direction of the cross product points into the page. And notice that is perpendicular to both A and B. So that is a property that's worth noting, that the resulting vector is perpendicular to both A and B. Into the page makes a 90-degree angle with both A and B in that particular example. It also shows how that sine factor comes in as well, right? If the angle between the two is 0, so suppose we have this example. And I have some vector A here. I have some vector B here. Now, by the right-hand rule, right, there really is no natural way for me to do that without kind of hurting my wrist. But then notice in this case then that, if I were to evaluate the magnitude of this vector, the angle between them is 180 degrees, sine of 180 is 0. And then similarly, if they were parallel to one another, so if I had, say, A, then I had B, right, I start pointing at A, I don't really have to move my fingers at all. And again, in this case, the right-hand rule really isn't telling you anything, because you just have to know that since the angle between them is 0, sine of 0 is 0, these have a 0 vector cross product. Both of these do, since the sine of the angle equals 0. So that brings us another test. So the test is if A cross B equals 0, for the dot product we said they must be perpendicular. Here this must imply that A and B are parallel or anti-parallel. Okay. Third and final, which room do I have? No room at all, is the actual computation of the vector. If it returns back a vector, then I should have some way to get components. Oh, actually, before I do that, let me make another note in terms of direction. Something that is very important. Let's just take the A and B. Let's go back up to this example here. Note if you do A cross B, right? So I do A, and I curl my fingers to B, my thumb points into the page. Now do B cross A. If I start with my fingers at B and curl up to A, notice my thumb points in the opposite direction. In, or out of the page in this case. Into the page when it's A cross B, B cross A, out of the page. Yeah, those are two different vectors. So the order matters in this case. A cross B is not the same as B cross A. You get two different vectors. They turn out to have the same magnitude, but they are anti-parallel to one another in this case. So that's different than the dot product note, right? Note the dot product, it didn't matter what the order was. Cross product, they do not commute. You cannot do B cross A and get the same answer as A cross B in terms of the vector. We should be able to see that when we do the computational form, is why I wanted to quickly go back. So the computational form of A cross B is summarized as the determinant of a 3x3 matrix. So essentially you have a 3x3 grid, and on the top line you write the unit vectors for x, y, and z. I'll use engineering notation, so I, j, k. In the next row you write the components of A, so ax, ay, az. Then the last row you write the components of B, bx, by, bz. And then this ends up, you take the determinant of this 3x3 matrix. Now, what's the determinant of a matrix? We'll save that for linear algebra. The computational way to do this is that you look down diagonals, and this is just kind of a rule you have to memorize. So, for example, the first component, the x component, ends up being ay bz minus az by, all in the x direction. The second component ends up being az bx minus ax bz, all in the y direction. And then the third component ends up being ax by minus ay bx, all in the z direction. Now where do these come from? And man, I don't want to memorize all that. Well, there's an easier way to memorize this. One, you can kind of notice that, in terms of this vector must be perpendicular to both A and it must be perpendicular to B. So notice, for example, the x component of this vector involved not the x components of A and B, but it's pulling from the perpendicular components, AY and BZ and AZ and BY, to create something. And then similar for the y component, it uses only Z and X, and the Z component uses only A and Y. So in these cases, right, that might help you kind of see how it is building to something that is perpendicular to both A and B. Now, the way to do this is you just look down diagonals. So you start with the x direction, and you go down the right diagonal till you get to the end. So in that case here. And then if your diagonal moves to the right, then it's a positive AY times BZ. So notice that then becomes this right here. Then you start with the x direction and you move down the diagonal in the other way. And you might have to loop around. So you have to loop around to something like this. And then if your diagonal is going to the left, you throw a negative sign in front of it. So notice that's AZ, BY, and there's a negative sign there as a result. Then you do it again for Y. Maybe I'll highlight this one. So we start with Y and we go down the diagonal and we have to loop around. And then notice that becomes this term right here. And then we go down the diagonal in the opposite direction. We have to loop around. And then that becomes this term here with a negative sign. And again, K, go down, loop around, that becomes this. And then K, go down the opposite direction, and that becomes this. So you're just going down diagonals. If it's to the right, you throw a plus sign in front. And then if it's going to the left, you put a minus sign in front. And that gives you the computational version of this. And then notice that since there is this minus sign, that then hopefully convinces you that the order does matter. Because 1 minus 2 is not the same thing as 2 minus 1. Right, so then that is why A cross B is equal to negative B cross A as a result. Same magnitude, opposite direction. So then if we go back to our example, which now that's on a different page, maybe let me copy this. Yeah, let's see. Let me copy it all. Copy. So then if I want to actually compute the vector C, how do we do that? Well, first thing I would do is I would write out the components of A and B. So the components of A and B, that's not too bad. I'll just skip right to the answer. So 3.88, comma 14.49, and 0 in the Z component. But the Z in this case might be in and out of the page. Let's write that. This is X, Y, and then Z would be in and out of the page. And B looks like it's going to be 9.06, 4.23, and 0. So then, if I want to do A cross B, I can write this out as a big 3x3 matrix, I, J, K. That looks like it's 3.88, 14.49, 0, and then 9.06, 4.23, 0. And what do I get? Well, these zeros actually make my life a lot easier. Because notice, I'll just do it one at a time. To compute the x component of C, I start here and I go down this diagonal. But oops, I hit a 0, so that's going to multiply to 0. Then I go here and I go down this diagonal, and oh, I hit that 0. So there's no x component. For Y, here I go down, I loop around, but I hit a 0. Then I go down the other direction. Oops, I hit a 0. So there's no x and y component, which makes sense. We said that the thing must point in or out of the page. In this case, for these particular two vectors, we argued that it should point into the page, which is not going to have an x and a y component. And then K looks like I go down. I'll actually highlight that one. For K, when I go down, and I loop around, and then I go in the opposite direction, In those cases, I do not hit a 0 at any point. So it looks like I then do, not highlighting, it looks like in that case, then I do what? Looks like I do 3.88 times 4.23 minus 14.49 times 9.06 in the z direction. So then I get, at the end of the day, so I get negative 114.9 in the k direction. That negative 114, that 114.9 should look familiar. That's the magnitude that we got. Since this vector only has one component, the magnitude of this vector is just 114.9. And this negative sign, the convention here is that that means it points into the page. And sometimes you will see this into the page is often written as kind of a circle with an X in it, versus out of the page, which is usually a circle with a dot. So now we have a way of determining magnitudes, direction, and the actual vector if we need to. So in this case, right, and again, notice this vector is indeed perpendicular to A and B. How could we test that? We could take the dot product if we wanted to. Right? If we did the dot product of A with C, we would get 0. If we took the dot product of B with C, we would get 0. Remember, that was the test. That, that shows that they're perpendicular. Yeah, so again, some other examples of this is that, just noting, when I say the convention of negative means pointing into the page, is that we want the right-hand rule to be obeyed by your coordinate axes as well. This is what's called a cyclic relationship. We don't worry too much about that. The math majors worry about that. So if you have x in this direction and y in this direction, they're perpendicular to one another. And note that when I do the cross product of x cross y, and again, right hand starts in the direction of x, sweeps up to point in the direction of y, looks like the resulting vector points out of the page. We can use that to define the direction of z. So then x cross y is z, which is out of the page. And the convention is that out of the page is a circle with a dot on it. I think the idea is that if I looked at an arrow tip from the side, right, an arrow tip on the side, that if I take that side tip and kind of look face down, right, I would see the tip of the arrow kind of surrounded by a circle. So that's out of the page, where then into the page is a circle with a cross. And then notice that this is obeyed also if you do y cross z. Right, again, start with my fingers pointing along the direction of y, curl them so that they're pointing out of the page. My thumb is pointing in the same direction as x. You should convince yourself that this is all true. Z cross x, I indeed then get y. So notice that there is a cycle here. Again, it's called a cyclic relationship. So now we have talked about kind of all the properties of the cross product. We can then tie this back to the magnetic force, which we said was Q V cross B. It satisfies all those experimental conventions that we kind of came up with, or experimental results rather, that we saw before. Now we can see kind of how this is encapsulated in the cross product. So in the example I did way back, right, where we were kind of experimentally trying to discover the direction of B, I had secretly assumed that B was pointing vertically downward. So again, when we had QB, where Q is positive, moving to the right. The direction of the force looks like I take QV, which is pointing to the right, and then I start with my fingers pointing in that direction. I curl them down so that they're pointing in the direction of B. Indeed, my thumb points into the page. F points into page. So as soon as it starts feeling that force, F is going to point into the page. Note that as it goes into the page and starts to rotate into the page, the direction of the force also changes as well, but we'll do that in the next lecture. If it was a negative charge instead, then the arrow would be pointing in the opposite direction. Notice that F then would point out of the page. And if you have an arrow going in this direction, that's QV. Then that curled down to B, thumb points out the page. When QV points perfectly downward, they're parallel to one another, there is no force. Yeah, so just a couple more examples and then we'll call it. Also, sometimes you draw your axes kind of with this kind of perspective. And here the convention is that's X, that's Y, and that's Z. First, note that the right-hand rule is obeyed. X cross Y points up to Z. Y cross Z points to X. Z cross X points to Y. But I'm going to need 3 of these. Just to give us 3 examples and then we'll be done. Yeah, suppose I have, I'm trying to do these before I get the answer. I suppose I have a positive charge that's moving this way and the magnetic field is pointing that way. What direction is the force? Suppose I have a negative charge that is moving this way and has a magnetic field pointing this way, the negative X direction. What direction is the force? And suppose I have a negative charge who is moving upward and then the magnetic field is pointing downward, both in the Z direction. What direction is the force? Well, for the positive charge, right hand starts along V, curls down to B. Looks like in this case then the force is in the positive X direction. Second one, I can take my fingers and curl and start them pointing in the direction of V, curl them up to B. Looks like then my thumb is pointing in the positive Y direction, but it's a negative charge, so I flip it. So it looks like then F is pointing in that direction. And then here, they're anti-parallel, so F would be 0 in that case. All right, so this is mostly a math lecture of getting some intuition, some familiarity with this cross product, which then we can use it to explore the nature of this magnetic force, both on charges and on wires next time.